Good afternoon, and welcome to the Embedded Executive Podcast. My name is Rich Nast, and I am with Embedded Computing Design. My guest on the podcast this week is Sean Park. He is the founder, the president, and the CEO of Point2. How you doing, Sean?
Hi, Rich. I'm good.
Very nice. Um, so this is going to be an interesting one for me and for the audience, obviously. We talk about a lot that data centers are popping up everywhere, and there's such a need to power these data centers, and they require a lot of power. So we talk about the GaN technology, the silicon carbide, and all the other power things that takes to power these data centers. What we don't talk about, I'll say ever, I don't ever remember having this discussion with respect to data centers, are the interconnects that are required to handle this massive amount of power. And that's exactly what you guys do. So let's talk about that a little bit. Am I on the right path with this? Is there some different technology that's required to handle the massive power in these data centers?
So basically, the number one power consuming component in AI data center is, of course, the GPU. So GPU consuming more than 70% of whole data center power consumption. And network interconnect, traditionally, it consumes only like a 10% of total data center power consumption. But these days, if you look at the like an NVLink, UL-Link, which connect multiple GPUs. In fact, it's connecting more than 100 GPUs. So there are more interconnects than before, and that interconnects consume a lot of power consumption. So there is some data showing how much it consumes, and it shows that 20 to 30% power consumption from network interconnect in AI data centers.
Would you be able to quantify that? Like, how much power are we actually talking about?
So, for example, NVLink, like a Blackwell GB200 system. So NVL 72, one rack has a 72 GPUs. And for that use case, there are more than 20,000 interconnect, and per interconnect is a 400 gigabit per second. So it's a lot of interconnect inside one rack. So one interconnect, I think it will consume around zero point 0.5 watts. So times 20,000 interconnects is a lot of power.
That's a lot of power. And then the next question, why isn't the technology we've been using before adequate to handle this?
So before we have used the copper interconnect, it's a passive copper. So passive copper, it means that it doesn't consume any power consumption, but some circuitries, some ICs need to drive that copper. And for AI data centers, data rate is 400 gigabit per second today, and it migrates to 1.6 terabit and 3.2 terabit. So speed is really, really high compared to before. And for that purpose, copper doesn't work anymore. So copper has limit on the bandwidth and also the reach of the cable lengths. And so copper doesn't work very well. So they need some active interconnect for that purpose. And typically optics work very well, but optics is very power hungry and very costly. And also it has a reliability issue. So that's why the power suddenly goes up really high in AI data centers.
Okay, back up just one step for me. Define the difference between an active interconnect and a passive interconnect.
Right. So passive meaning is passive copper. So active, there are various forms in products. So typically they can increase the reach of the copper cable, adding some active devices in copper. So that we call active copper cable or active electrical cable. So that one, we need to add a DSP or retimer on copper cable. So
Hmm.
that consumes some powers. And more power hungry solution is optical cable. So optical cable require laser photo detector that we call OSA. On top of that, of course, we need a DSP and retimer. So it's more power hungry than active copper solution.
So if you're not using copper, what are you using?
So our approach is very different. So copper has limitation in terms of bandwidth and reach, and optics has reliability issue, power hungry, and too expensive. So we came up with so-called E-tube solution. E-tube is RF signal over plastic cable. So it's a full monolithic solution, meaning that we're still using silicon. We don't require any external laser or photo detector or gallium nitride or indium phosphide, that kind of compounds. We don't need that. So it's pure silicon solution. And we send that RF signal over plastic cable so that we don't have any DSP, we don't have laser photo detector. So form factor is very simple, BOM is simple, and the power consumption is only one third of an optical solution.
Okay. So one of the things I've learned over my years is that
Mm.
everything comes with a trade-off.
Yeah.
What are the trade-offs here?
So compared to optics, we can address like a scalar market, which is under 10 meters. And over 10 meters is kind of difficult in terms of technology itself. So we intentionally target under 10 meters, and over 10-meter market is optics market.
Okay. And what about the costs involved?
So cost is very close to copper cost because cable structure itself is similar to copper. And on top of that, we adding RF devices, which is, like I said, is full monolithic silicon device.
Okay. A lot of the folks who would be deploying this technology would not do this without a second source.
Right.
What's going on with respect to that?
So in terms of cable manufacturing, we are working with more than three cable manufacturers. So Molex is one of them. So also Molex is our strategic investor. So they're all making these waveguide cables for E-tube solution.
Okay. So to be clear, are you producing the interconnects or are you licensing the technology?
We licensing this technology to cable manufacturers. So we own E-tube platform, but we only sell ICs to cable manufacturers.
Got it. And are you working through any of the standards bodies?
Not yet, but we plan to do that because we want to expand our exposure to many different places in the market and in the standard bodies as well.
Very interesting. So is the technology available from your partners today?
We have POC, so but at the end of this year, we are going to release the 1.6 terabit solution, and 1.6 terabit solution will be in production sometime next year.
That is very impressive. I look forward to seeing it when it comes out.
Yeah, that'll be very interesting to me as well.
Thank you very much, Sean. I appreciate you taking the time, certainly to educate me, but to educate the audience as well.
Great, thank you, Rich.
That was Sean Park. He is the founder, the president, and the CEO of Point2, and I am Rich Nass with Open Systems Media.